Let's take a look at the mole to particle conversion and reverse. So we're going to take the number of moles and we're going to figure out how many particles there are. So that particles might be molecules or atoms, hockey pucks, whatever. So let's look at this. Calculate the number of atoms in 5.5 moles of sodium. So our conversion for this is 1 mole equals 6.02 times 10 to the 23 particles. Right, so this is our conversion rate. So in this question, we know our moles. So I know my mole of Na. And I'm going to try to figure out the particles of Na. So I know my moles is 5.5. And that has two significant figures, 5 and 5. So now I do this. I set up my conversion. How many particles of Na are in 5.5 moles if there are this many particles, 6.02 times 10 to the 23 particles in 1 mole? Now, I haven't talked about this, but you know you're doing this right when you have the same units on the top and the bottom, right? Moles on the bottom, particles on the top. It should always be that way. All right, so I just do 5 times 6.02 times 10 to the 23. So I got to get my calculator out. And so I'm going to do 5.5 times and equals 3.311 times 10 to the 24 particles. My number of particles is 3.311 times 10 to the 24. So my particles is 3.311 times 10 to the power of 24. This should have two significant figures for my answer. So I'm going to round it so it has two significant figures, 3.3 times 10 to the 24 particles. All right, so you can tell this is a lot simpler than having to do all the molar mass conversions. All right, so let's take a look at the second example, which will just be the flipped. I have 1.0 times 10 to the 22 molecules of a compound. How many moles is that? So this time we know our particles of whatever, and we're going to go to our moles of whatever. And we're going to use the Avogadro's constant to do that. So how many particles do I have? I have 1.0 times 10 to the 22, and that is two significant figures because zeros, trailing zeros after a decimal are significant. Now I set up my thing. How many moles are in 1.0 times 10 to the 22 particles if 1 mole has 6.02 times 10 to the 23 particles? So I'm going to do this 1.0 times 10 to the 22 times 1 divided by that. And I'm going to get, when I do that, 1.0 times 10 to the power of 22 divided by 0.0166. So my moles, 0.0166 moles. So I'm going to write that down over here, 0.0166 moles. And this guy's got to have two significant figures. So we need to keep those two significant figures, so we round this to 0.017 moles. There we go. These conversions are much, much simpler. But now we're going to take it up a notch. All right, let's look at this guy. Okay, calculate the number of calcium and phosphate ions there are in 2.5 grams of calcium phosphate. Now, I don't know why I put this one here, but I did. This is a two-step conversion. Okay, this is why we map it out. What do we know from the question? We know mass of calcium phosphate. And calcium phosphate is Ca. Oh, please don't be. Oh my goodness, this is not fun. Calcium phosphate. Oh, this one's going to be fun. It's Ca3 PO42. PO42. So we're going to start with the mass of calcium phosphate. Then we're going to go to the number of moles of calcium phosphate, Ca3PO42. Then from the number of moles, then we're going to go to the number of particles of Ca3PO42. We're going to do 2. The first one we're going to do using the molar mass, and then we're going to do the second one using Avogadro's constant. Now the reason this one's not a lot of fun is because we've got to do the molar mass of this. And you know what? I'm just going to put on a sticky note so that I can do this right here and then take it away so I've got more space. So we need to do the molar mass of Ca3PO42. So we do our Ca, calcium, is 40.078, 40.078, times it by 3. Then we do our P. There's 3 of those. There's 2 P's. So phosphorus, 30.974, and we times that by 2. There's 2 phosphorus. Then O, we have 8 O's because it's 4 times 2. 15.999 times it by 8. Grab out the old calculators. We start doing this. 40.078 times 2 is equal to 80.156. 30.974. Oh, I times that by 2. I need to times it by 3. No, not 23, just 3. 120.234. Then my P, I times that by 2. 61.948. And then my last one, 15.999, times it by 8 to get 127.992, and total that up, plus this is equal to 310.174 grams per mole. All right, I left it out here so that I could refer to it down here. So the mass I know. We know the mass is 2.5 grams and 2 significant figures. All right, so now we've got to go from mass to moles. So I start by writing how many moles are there in 2.5 grams if 1 mole has 310.174 grams. Now I work this out. 2.5 times 1 divided by 310. 0. So my moles is equal to 0.00806. Keep that number in your calculator. We're going to write it up here, 0.00806, and it should have 2 significant figures. It's got 3 significant figures. Okay, so when we're doing a question with multiple steps, we have to keep one more or two more significant figures than our final answer will require. Our final answer is going to have two significant figures. So we need to keep three significant figures in our intermediate steps. And then I just like to keep it like this. I write this down, but then I keep this number in my calculator. Now we're going from moles to particles. Okay, well, let's write up our conversion for moles to particles. So I start with particles because we don't know how many particles are there in 0.00806 moles, right? All of this comes from here. If there are 6.02 times 10 to the 23 particles in 1 mole. So I have to take this and multiply it by that. So I take this and I times it by my 6.02 times, and I get 4.852 times 10 to the 21. 4.852 times 10 to the 21. 4.852 times 10 to the 21. Now, this guy should only have two significant figures, our final answer, because our first guy only had two significant figures. So this should become 4.9 times 10 to the 21 particles. Whew. It's a long question. So you can see there's a two-step conversion. And the most we ever get to once we get to stoichiometry, a full question will have probably 5 steps. So 1, 2, 3, 4, 5, maybe only 4 steps. 4 or 5 steps will be the longest conversion chain you'll have. And as long as you map it out like this and you understand how to get from one step to the next step, you'll be fine. All right, so next one. A little different question. Consider 4.0 moles of C5H12. How many molecules are present? Well, we know our moles. I'm going to map it out. Moles of C5H12. So how many particles of C5H12 will we have? Avogadro's constant will get us that. We know that this is 4.0 moles, two significant figures. So let's set up our conversion. How many particles are in 4.0 moles of something? If there are 6.02 times 10 to the 23 particles in 1 mole. Eventually you'll get to the point where you just know that I multiply those two together. It's not really complicated. So I'm going to do this number times 4. 2.408 times, I wrote this down way wrong, 2.408 times 10 to the 24 particles. And it should have two significant figures because this guy had two significant figures. So 2.408 times 10 to the 24. So our final answer here would be 2.4 times 10 to the 24 particles. Okay. Now, this question is how many carbon atoms are present? Well, we have this many molecules, right? And each molecule has 5 carbons. So we have 2.408 times 10 to the 24 molecules. And there are 5 carbons in 1 molecule. So we just multiply that out. So we take that number, we times it by 5 to get 1.2 times 10 to the 25 carbon atoms. So how many H atoms are present? Well, we have 2.408 times 10 to the 24 molecules. And there are 12 hydrogens in one molecule. So that times 12. So my 2.408, and I times it by 12. 2.989 times 10 to the 25. H atoms. Right. So you're able to work with the number of particles and converting from the number of particles to the number of moles. All right, thank you for watching. See you in the next video.